Hello. We've been solving equations, so now we're going to look at inequalities, which are very similar to equations, but there are a few slight differences. And so the goal for this lesson is to be able to graph inequalities with the number line, and we're going to solve what I consider to be the simple inequalities. If you've already had an algebra 1, you should still be able to do one-step, two-step, multi-step, like where you got to combine like terms or distribute variables on both sides. These aren't going to be too challenging for you since we just reviewed equations. The only tough part's going to be about, doing number line graphs, and you might remember that sometimes you have to reverse the inequality symbol as part of doing the work for these. And so we got to make sure you remember all the times when you should do that. Well, what is an inequality? It's a statement that compares unequal quantities. Equation means equal. Inequality obviously means not equal. These are sometimes called order relations. You don't hear that a lot, but if you were sitting in freshman college math, your math professor starts talking about order relations, and then he starts putting these symbols on the board, maybe you'll remember I mentioned that sometimes they get called order relations instead of inequalities. You should be familiar with these 5: greater than, less than, greater than or equal to, less than or equal to. And this one you should know, but for whatever reasons, just don't think of this necessarily as an inequality. But the name means, inequality, not equal to. Excuse me. We need to start with sort of one of the big ideas of inequality is something called the trichotomy property that says that for any two real numbers, they can be compared in one of exactly 3 ways. In other words, for any two numbers, one of the numbers is less than the other, they're equal, or the number you're thinking of as the first number was actually greater than the second number. And so trichotomy literally means to cut into 3. And so when you think about it, what you have is like the less than or equal to symbol is actually a way of saying I'm not sure which of these top 2 conditions are true. The greater than or equal to symbol is a way of saying I'm not sure which of these 2 conditions is true. That's why you got to emphasize the word there is or. Strict inequality. I won't use this phrase a lot, but I've heard it used by other people a lot, and that's just when you're trying to really just stress that or equal to isn't there. Strictly greater than, strictly less than. So what about solutions of inequalities? Well, kind of like with equations, it's going to include any value of the variable which makes the inequality a true statement. Therefore, most inequalities, by their nature, actually have infinitely many solutions, and you cannot really list the solutions. So what we usually use is sort of a visual representation of the solutions of an inequality, and that's the number line graph. And it's a set of points on the number line, and it might look like a segment or array on the number line, and it's going to have endpoints that are open or closed. And you might remember that open's like empty or not filled in, so this is an open fist. Closed is solid and filled in. This is a closed fist. You use open when the endpoint is not a solution. You use closed when the endpoint is a solution. So open is either going to be a greater than or a less than. Closed is going to be or equal to's. So real quick, which inequality is represented by each of these graphs? Which inequality is represented by each of these graphs? This is an open endpoint at 2 that is pointing to the left. So this is x is less than 2. X is less than 2. Let me draw to open doodler. Can make doodler smaller. So this first one is x is less than 2. See if I can change the writing one here. Okay, the next one. Well, if you can agree with the top one being x is less than 2, you're probably not terribly shocked that this next one is x is greater than 2. Point of emphasis here, if the variable's on the left-hand side of the inequality, then the reason why we use this symbol, the kind of arrowhead, is that it represents the tip of the arrowhead on these rays. And so less points left, greater than points right. This is a closed endpoint, so this next one would be x is less than or equal to 2. That's closed and pointing right, so it would be x is greater than or equal to 2. And then we have a couple other questions here real quick. So how would you graph x equals 2, you might wonder? Okay, well, we know that x is equal to 2. And when I do number line graphs, I always do them sort of above the number line so that they're easier to see. But they should be on the number line. I'm just making it easier to see. And we're not less than, so we're not pointing left, and we're not greater than, so we're not pointing right. It's simply a matter of a closed endpoint, and there's nothing else to it. So this would be x equals 2. And you know, before you ever saw the inequality graphs, you were graphing x equals 2 on the number line. You were just going to 2 and putting a point. But you know, that might have been second or third grade since you saw that last. What about x is not equal to 2? Well, we're going to have an open endpoint at 2 because we're not equal to 2. And you know, 1's not equal to 2, and 0's not equal to 2, and negative 1's not equal to 2. And so here's 3 solutions, but so is 1/2, or 1.8, or 1.2. And so next thing you know, well, wait a minute. 3 is also a solution, and so is 4, and 2.5, and 7. And so the common theme here is that you got solutions going in both directions. And so that's actually the graph of x is not equal to 2. It's the open endpoint at 2, and then it points in both directions. So it's both. This is actually a combination of x is less than 2. I'm going to run out of space at the bottom. Or x is greater than 2. Just like in a way, this one appears actually a combination. X is less than or equal to 2. And instead of or, x is greater than or equal to 2. Of course, not many people are going to really think of it that way because it's much simpler to just say that x is equal to 2. But it is worth mentioning that if something that you don't know is less than or equal to a number and greater than or equal to the number, then it's actually just equal to the number. So that's kind of strange but true when you think about it. Okay, let's hide that. Okay, so back to the PowerPoint here. Properties of inequality. Well, these names are going to look kind of similar to some of our properties of the equal symbol. We had reflexive, symmetric, transitive, but the only one that has the same name for inequality is transitive. So the only one that still works the same way is the transitive property. Ir and anti are both prefixes that might mean like not, or anti is actually like against. And so we've got the not reflexive property says that for no number a is greater than a. Yeah, that'd be nonsense. There isn't a number that's greater than itself. The the against symmetry property or anti-symmetric property says that if A is greater than B, then B is less than A. And as soon as you chew your eye this with like a couple of numbers, it makes complete sense. If 5 is greater than 3, 5 is greater than 3, then 3 is less than 5. Transitive property, however, works the exact same way. If 5 is greater than 3, then 3 is greater than 2, then 5 is greater than 2. You can cut out the middleman and sort of move straight from the A to the C. Remember, trans means move. Here are some other properties of inequality. It turns out inverses reverse an inequality. Inverses reverse. Say that 5 times fast. Inverses reverse. Inverses reverse. We'll pretend that's 5. If you do an opposite on both sides of an inequality, it reverses the inequality. So if you have A is greater than B, then the opposite of A is less than B. The idea is if you change the signs here, it reverses the inequality. By the way, I'm phrasing these inequalities for greater than, but I could rewrite a new version of these for the other inequality symbols like less than and the or equal to's. Let's look at back to do for a second. I want to say something. Let's clear that out. Opposites property, make sure you agree. Everybody knows 5 is greater than 3, but as soon as I change both signs, oh, wait a minute, that would be less than. We got something similar happening for reciprocals. If A is greater than B, then the reciprocal of A is less than the reciprocal of B. So it's like the same. 5 is greater than 3, but if we reciprocate both those numbers, hopefully you know that a fifth is actually a less than a third. And so if you're really comfortable with numbers, both of these make complete sense. But for those of you that have a little trouble with negatives or fractions, you might have to actually stop and think about these and convince yourself. Okay. We won't use the reciprocal one nearly as much as we'll use the opposites one, but I thought it would make more sense if I showed you that in both cases, an inverse, either opposites or reciprocals, actually reverses this inequality symbol. Reverse, reverse, which now sounds like you're maybe doing the cha-cha slide. For people that, would line dance. I don't line dance. Not that you all are terribly shocked by that. Okay. Here's an addition property of inequality. If A is greater than B, then A plus C is greater than B plus C. You can add the same thing on both sides. And I'm not going to do a subtraction property because at this point I think you all are fairly comfortable with the idea that a subtraction is really addition by a negative, so we don't really need a subtraction property. But technically, if A is greater than B, then you could also say that A minus C is greater than B minus C. Inequalities do, however, kind of this neat property here. If A is greater than B and C is greater than D, if you add the left-hand sides together, it's still guaranteed to be greater than the right-hand sides added together. And again, I'll just use Doodler real quick to kind of give you a feel for that one. We know 5 is greater than 3. We know that 7 is greater than 2. So we're not terribly shocked when we add the left-hand sides and the right-hand sides and get that 12 is greater than 5. Yeah, that's common sense. And so the point is that when you add the big things and you add the small things, the big things together are still greater than the small things. But part of this is pretty clear for nice numbers, but the point is that it's still going to be true even if you start throwing in negatives or fractions or decimals. And then multiplication. If A is greater than B and C is greater than 0, by the way, the C is greater than 0. That's a fancy way of saying that C is positive. So if A is greater than B, excuse me, and C is a positive number, then A times C is greater than B times C, which of course just begs the question, what if C is negative? So if A is greater than B and C is less than 0, C is negative, then when you multiply by a negative on both sides, it ends up reversing this inequality. So let's put these properties of inequality into effect here. Let's work these problems. Well, we would subtract 7 on both sides, and 9 minus 7 is 2. And we want x by itself, so we can change the signs on both sides using the opposites property, but that forces us to reverse the inequality. And we don't want to just solve these, we also want a graph. So quick number line graph. Here's what I need to see for your number line graphs. I need to see the number in question and some sort of scaling that is accurate. But I don't necessarily have to see 0. Some of you all are, you want to see 0. But what if the numbers you're using are, really, really far away from 0, like 713. I don't want to see 713 tick marks. So you either got to get creative with your scaling or just show me part. And let's see, this would be an open endpoint, and it would point to the left. So there's the number line graph. So all of this together, is the solution. Here's the solution as an inequality. Here's a visual representation of that solution. So we know that things like -3 or -2.7 or -17 or -3,281 would all make this a true statement. Alright, so in this next example, let's see, we want to get rid of subtraction by 3, so we would add 3. And let's see, you'll never reverse inequality from adding or subtracting. So add 3, 6 and 3 is 9. And let's see, we divide by 2 to get rid of that multiplication. And half of 9, a lot of you would say, is 4.5. So here's what you can show me in terms of a number line graph. Or this one. Here's 4. Here's 5. Here's 4.5. We would need a closed end point, and it's less than, so it's pointing left. All of that is the complete solution. Or actually, I shouldn't say complete solution, because in a later lesson we'll actually even add on an extra piece to this. But for right now, this is the complete solution. Alright, so here's one where we've got variables on both sides. So from our work on equation solving, we know that we probably want to get our variables together first. So I want to actually subtract 2x on both sides. And I do kind of still show you all that bookkeeping. So I'll show you the bookkeeping on the subtract 2x. So it's 3x minus 7 is less than 5. Well, we would add 7 to get that 3x is less than 12. Divide by 3 on both sides. X is less than 4. Number line graph. Oh, let's show 3, 4, and 5. It would be an open end point pointing to the left. What's a way to check this, you might wonder? If you don't remember, the way to check this is you take a number, like say 3, that should be a solution, and you go back to the original problem. So let's talk our way through a check real quick. 5 times 3 is 15. 15 minus 7 is 8. 2 times 3 is 6. 6 plus 5 is 11. And sure enough, 8 is less than 11. It's not a perfect check, but it does give you a chance of being sure you're correct. You would check, if you want to be really thorough, you check a couple values that should work, a couple values that shouldn't work, and make sure that you've got the problem solved correctly. Here's our solution. You probably don't like this one because of the division, so you fraction bust. and multiply by 2 on both sides. And those cancel completely to 1, and 1 times 5 minus x is still 5 minus x. And 3 times 2 is 6. So now you would subtract 5 on both sides. Opposite of x is less than. 6 minus 5 is 1. Change signs on both sides using the opposites property. However, when you do that, you must reverse. Must reverse. And then let's see, a number line graph. Show you -2, -1, 0. It's greater than, so it's open, it's pointing to the right. Alright, how about this one? Ooh. I mean, ask yourself the question, what would you do if this were equals? However, please, oh please, oh please, do not make the rookie mistake of actually changing it to an equals, working the problem, and then putting that symbol back in at the end. Because their inequality could theoretically reverse direction a couple different times during the problem. There's no way to keep track of that if you're not actually writing it each step. And so I have every year a student or two who at some point got into this bad habit of changing this to equals, pretending it was equals, which I'm fine with, just to get an idea of what to do next. But instead of just pretending it's equals, they actually change it to equals, and sometimes it causes some problems. We would probably distribute first on this problem. So let's go ahead and do that. 12x, distributing a -2, be minus 2x minus 10 greater than or equal to 21x plus 45. A couple of you might be going, but wait a minute, we multiply by a negative. Why aren't we reversing the inequality? We did not multiply by a negative on both sides of the inequality. We did not move a negative across the inequality. All we did was within one side of the inequality distribute a negative, and that's fine. Let's see, 12x minus 2x is 10x. Minus 10 is greater than or equal to 21x plus 45. I want to get my x's together. 21 is more than 10, so I'm going to subtract 10x on both sides. I like to keep my coefficients positive, as you might remember from the equations video. These cancel to 0, so it would be 0 minus 10 is -10, greater than or equal to 11x plus 45. Now at this point, some of you might be a little panicked because the variable's over here on the right. That's okay. We'll be alright. If it's really bothering you, turn the whole thing around. Subtract 45 on both sides. -55 is greater than or equal to 11x. Divide by 11 on both sides. -5 is greater than or equal to x. Well, we want x in front. So if -5 is greater than or equal to x, then by the antisymmetric property, x is less than or equal to -5. And let's see, -6, -5, -4. It is closed and pointing left. Had a lot pointing left tonight. Just so happens they got to point either right or left, and most of these have pointed left. Last one, and maybe you haven't done one like this before, but it's the same basic idea. Solve it like that were in equals. Draw a number line graph. So we got two different distributions to do here. 10 minus 5x plus 3x minus 2 is not equal to. Got to carry that not equal to from step to step to step. Well, let's distribute -2, -6x, see, negative 2 times positive 2 would be minus 4 plus 5. Now we got some like terms to combine on each side. Let's see, 10 minus 2, 10. Actually, let's do that in red. 10 minus 2 is 8. Then, it didn't work out so hard. Let's try to double it on. Oh, it worked much better that time. Negative 5x plus 3x would be minus 2x is not equal to. So I got all this space. I'm going to keep my not equal to's kind of lined up so that it's very clear what the two sides of the inequality, the not equal to. Oh, we've got a couple like terms right here. Negative 4 plus 5 would be 1, so negative 6x plus 1. I like to keep my variables positive. I need to get them together. I'm going to add 6x on both sides. And we'll see if I can't do that without showing you the bookkeeping. I'm going to start breaking you with the bookkeeping on that. So we add 6x on both sides. Well, they're going to cancel over here, and negative 2x plus 6x would be 4x. So 8 plus 4x is not equal to 1. Subtract 8 on both sides. 4x is not equal to subtracting 8. So 1 minus 8 is negative 7. Divide by 4 on both sides. Cancels to 1x or x, negative 7/4. Okay, number line graph. Let's see, negative 7/4 is not quite negative 2. Negative 8/4 would be negative 2. So here's negative 2. Tick, 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 tick. There's negative 1. Tick, tick. Let's see, this would be negative 4/4, negative 5/4, negative 6/4. Negative 7/4 would be right here. It would be open, and it would point in both directions. And so there's your number line graph. Alright, how was that? Hopefully you found that it was just like solving equations, except with the couple added wrinkles. We've got to make a number line graph, and we got to remember when to reverse inequality. So, when do you reverse the inequality? When inverses are involved. And so for us, that usually means you multiply or divide by a negative. You must reverse the inequality. So here we go. Here's what, people know this, but they mess up. Here are the things you need to remember about reversing. If you turn the whole inequality around, that's the antisymmetric property, and you've got to reverse the inequality. If you change the sign on both sides, you take the opposites, you've got to reverse the inequality. If you take a reciprocal on both sides, you must reverse the inequality. We probably won't use that much, but it's true, so I want you to know it. Or if you multiply or divide both sides of an inequality by a negative. If you're not sure if you should reverse inequality, what you can always do is go over into the margins. Wow, that's obviously not what I meant to create. Alright, you can always go over to the margins and do this. If you're not sure if you should reverse inequality or not, take two numbers, compare them in the way you know to be true, and then, I know this is true, but say you take a negative on both sides of solving an inequality problem. and you're not sure whether or not to reverse. Well, if you take 3 is less than 8, and you do, well, let's reverse both signs. Hopefully you can remember that one reverses, so yours will reverse too. Or you take reciprocals. Oh, well, a third of a pizza is more than an eighth of a pizza, so that reverses. Or you reciprocate both. Oh, wait, that's what we just did. What am I saying? Wow. It's a little bad. It's getting late, I guess. Sorry about that, you all. We already reciprocated both. There, it's like it never happened. White out. Let's say you take, go back to the brush though. So you take both sides and multiply it by 2. You'd have 6 is less than 8. Oh, okay. 6 is less than 8. So you don't need to reverse inequality and multiply by 2. But if you multiply by negative 2, you would have negative 6 and negative 8. And that's greater than. And so when you multiply by negative, you would also have to reverse the inequality. Alright, so that's getting a little long, but wanted to review all the different ways you might have to reverse the inequality. Alright, so here's the overview. Let's wrap it up real quick. Solving inequalities is just like solving equations. You might have to distribute first and then combine like terms, and then you might have to get your variables together on one side, and then you'll cancel an addition and subtraction. And then this fifth step is kind of where it gets interesting. If you cancel multiplication or division and it involves a negative, remember to reverse that inequality symbol. Remember to graph a solution on the real number line. And then I didn't do a great job of this while I was modeling it for you. I only really did it on one problem. But you should always check a solution just to be sure you're right. And so I kind of didn't do such a hot job of modeling that, so I'll slap myself on the hand, kind of say bad teacher. Alright, I believe that's it for right now. I'll talk to you later. I'll see you in class. Hopefully this made good sense to you. Thank you for your time.